Today we're going to look at 10.3, which is separable differential equations, and we're going to find both general and particular solutions. So let's define what a separable equation is. A separable differential equation is one in which all the x's and dx's can be separated, that's literally what we're doing here, from the y's and dy's. And so usually this is done by having a first order differentiable equation in the form dy over dx is equal to g of x times f of y. And so we have a product of x factors and y factors. Sometimes you also see a quotient of x factors and y factors, depending on it. If I have it as a quotient, so long as I don't have f of y equaling 0, we can kind of rewrite as long as I have a product, so long as f of y is not equal to 0, I can kind of rewrite it into this fraction situation where h of y is 1 over f of y. And basically, our goal on this will be to separate and then integrate. So here I have it as a quotient, and I'm going to start by cross multiplying. So we'll have y squared dy is equal to x dx. So they're separated. Notice all my y's are on the left and my x's are on the right. And then I'm going to integrate. So again, separate and integrate. So I find the antiderivative of y squared is 1/3 y cubed. My antiderivative of the x is 1/2 x squared. Now normally I would have plus c and plus c, another constant, maybe d, on both sides. But those two constants can be combined together, and we'll just write 1 plus c, and I like to put mine with the x's. At this point, we can sometimes we leave our answer in an implicit curve, and sometimes we solve it. One other thing, part B asked us to use this initial condition. So this is saying that we have the value 0, 3, and I want to find what c is. So I'll have 1/3 3 cubed is equal to 0 c. So 1/3 times 27 is equal to c, so therefore c is equal to 9. So if I left it as an implicit curve, I'd have 1/3 y cubed is equal to 1/2 x squared plus 9. If I was writing explicit curve, which I could do on this one because I have just y cubed, I'd have y cubed is equal to 3/2 x squared plus 27, and then y is equal to the cube root of that. I don't know if it necessarily makes sense to rewrite it. Sometimes it does and sometimes it doesn't. It depends on whether it tells you more information in one format or another. Here's another one. And so you can see on this one I have everything on the left, which is a little weird, but I'm just going to multiply both sides by this piece. So I've got y cubed plus y dy, that parentheses, is equal to x squared plus 3x times dx. So they're separated, and now I'm going to integrate. Separate and integrate. So 1/4 y to the 4th plus 1/2 y squared equal to 1/3 x cubed plus 3/2 x squared plus c. At this point, I am not going to solve for y. I'm going to leave this as an implicit curve because I have y to the 4th and y squared, and that will not solve nicely. Y dx is equal to xy plus 2y. But wait, you said at the beginning that it should be a product. I currently do not have a product, but I can factor it. It is a product. Yx plus 2. So then when I separate, I'll have dy is equal to y plus 2 dx. So that was just multiplying both sides by dx. Now I'm going to multiply by 1 over y. 1 over y is equal to x plus 2 dx. So now I have separated, and now I'm going to separate and integrate. The integral of y is ln, and the antiderivative of 1 over y is ln of absolute value of y. It's equal to, I have 1/2 x squared plus 2x plus c. Again, I'm only putting one constant because the two constants could have combined. From here, if I wanted to get this to be isolating y, I have absolute value of y is e to the 1/2 squared plus 2x plus c. And that's just converting back to an exponential equation. We'll look more at those in depth in the next section with applications. So we could also have them written in this format where I have y prime, but I'm just going to start by writing y prime as dy dx. And I'm going to separate. Separate, get my y's on the left, x is on the right, and then integrate. So ln of y is 1/3 x cubed c, and isolate y when possible. One last thing to talk about, and that is orthogonal trajectory. So it's a curve that intersects a family of curves orthogonally at right angles. So you see here I have a bunch of circles. That's a whole family of functions with different radii. And these lines that I have drawn in all intersect those circles at 90 degrees. So find the orthogonal trajectories of the family of curves x is equal to ky squared, where k is an arbitrary constant. Well, x equals ky squared is a bunch of parabolas that are all going to kind of look like this. Okay, and then like that, and so on. Okay, so the first thing I want to know is what the derivative is. So I'll take the derivative on both sides, and so I'll have 1 equals 2k y prime. Okay, that's using an implicit differentiation. And so y prime is equal to 1 over 2ky. Well, if I rearrange this original for a moment, that's telling me k is equal to x divided by y squared. So if I use a substitution, I can have 1 over 2, replace k as x over y squared. Now I'm going to have y prime is equal to 1 over 2x over y. Multiply top and bottom to get rid of that complex fraction. Y prime is 1 over 2x. So the reason I did that was I eliminated the k for whatever that arbitrary constant is. Okay, so now I've gotten rid of that. Now, I wanted something that's orthogonal or intersecting at right angles. We've also thought of that as perpendicular. We avoid calling it perpendicular here because we're not talking about lines. Two lines are perpendicular, but curves are orthogonal. But if I use that same application, something that would be intersecting at a right angle or almost perpendicular would be 2x, would have the slope negative 2x over y, because I found the opposite reciprocal. So now I'm going to work with dy dx equal to that perpendicular or orthogonal slope. And now I'm going to separate and integrate. So I cross multiplied to, and now I'm going to integrate. Get 1/2 squared equal to negative squared plus c. I'm going to move everything onto one side, so I get x squared plus y squared over 2 equal to c. And rather than solve that, I'm going to leave it as an implicit curve because this tells me more information about it than if I had it solved. This tells me we're looking at ellipses. So if I had a bunch of parabolas, I could draw these ellipses, and you have this over 1 so that you can see it in that format, and they would all intersect at 90 degrees. And that concludes lesson 10.2.